You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Speech pipelines are the systems that make it possible for machines to handle spoken language in ways that feel natural, useful, and interactive. They involve the transformation of sound into text, the structuring of conversations into recognizable participants, and the regeneration of synthetic speech back into audio that humans can hear. At their simplest, a speech pipeline connects three critical components: automatic speech recognition, speaker diarization, and text-to-speech. Together, these create a loop where human speech enters as sound, is processed into structured meaning, and returns as audio output. The importance of these pipelines lies in their ability to bridge communication between humans and machines in real time, turning voice into a practical medium for interacting with technology. Without pipelines, voice assistants, transcription services, and accessibility applications would not exist. With them, spoken language becomes an input and output channel as central as keyboards and screens. Automatic speech recognition, often shortened to ASR, is the foundation of most speech pipelines. Its role is to take audio signals and translate them into written text. This process involves analyzing waveforms, breaking them into frames, extracting acoustic features, and matching those features against models trained on massive speech datasets. The leap from raw sound to text requires complex statistical inference, since the same word may sound different across speakers, contexts, or environments. Modern ASR systems rely heavily on deep learning, with neural networks modeling both phonetic details and linguistic context. For example, if a user says "recognize speech" but the audio is noisy, the system must determine that the phrase is more likely than "recognize beach." This disambiguation illustrates how ASR does more than hear sounds. It interprets them in meaningful, context-sensitive ways that humans expect. The accuracy of ASR is influenced by a host of factors, and this is where real-world deployment becomes challenging. Clear, high-quality audio makes recognition easier, but background noise, low-quality microphones, and overlapping voices quickly degrade performance. Accents and dialects present another major challenge. Systems trained mostly on standard accents may struggle to handle diverse speech patterns, producing errors that frustrate users. Speaking speed and clarity also matter. Fast, mumbled, or slurred words are harder to interpret. Domain vocabulary plays a role as well. Specialized terms in law, medicine, or engineering often fall outside general-purpose ASR models, leading to misrecognition. Addressing these issues requires careful dataset curation, fine-tuning on domain-specific material, and continual adaptation to real-world conditions. Accuracy is not an abstract metric but a lived experience, determining whether users feel understood or alienated by a system. Speaker diarization brings additional structure by distinguishing who is speaking in a conversation. This task is often described as answering the question, "Who spoke when?" Rather than producing a block of undifferentiated text, diarization segments audio into labeled portions attributed to different speakers. This is essential in settings like meetings, interviews, or multi-party phone calls, where attributing words to the right person carries legal, professional, or interpersonal significance. Technically, diarization analyzes patterns such as pitch, timbre, and pause length, clustering similar voices and separating distinct ones. The result is a transcript that reads like dialogue, with each contribution tied to the correct participant. This capability enriches ASR outputs, transforming them from raw text into structured records of interactions. Without diarization, transcripts lose much of their usefulness in collaborative or regulated contexts, where speaker identity matters. The applications of diarization demonstrate its growing relevance. In business meetings, diarization ensures accurate notes, making it clear who proposed an idea or made a decision. In call centers, it enables detailed performance analysis by distinguishing customer speech from agent responses, supporting training and compliance. In journalism, diarized interviews allow reporters to quote sources accurately, reducing the risk of misattribution. Even in academic research, focus group transcripts benefit from diarization, helping analysts track how ideas move between participants. Beyond convenience, diarization provides accountability, clarity, and precision. It mirrors the way humans naturally perceive conversation as a set of turns between participants, rather than a single, undifferentiated flow of words. Text-to-speech, often abbreviated as TTS, is the component that closes the loop in a speech pipeline by turning written text into spoken output. TTS has advanced dramatically in recent years. Early systems produced stilted, robotic voices that were often unpleasant to listen to for long periods. Today's neural models generate speech with prosody, intonation, and rhythm that approach human naturalness. These advances allow TTS voices to express nuance, such as rising inflection for questions or pauses that signal commas and periods. Applications range from voice assistants reading out responses to accessibility tools that vocalize written content, to public announcement systems that provide instructions or updates. The key contribution of TTS is enabling machines to speak back, completing the cycle of natural interaction where communication flows in both directions. The naturalness of TTS is a critical determinant of its effectiveness. Listeners are highly sensitive to prosody, the melody of speech that signals emphasis, emotion, and structure. A system that reads text in a flat monotone may technically be intelligible, but it fails to engage or comfort the listener. Consider the difference between a robotic "your train is arriving" and a natural, well-paced version of the same phrase. The second instills confidence, while the first may cause doubt. Capturing these nuances requires training models on vast amounts of high-quality audio, paired with transcripts, allowing them to learn the patterns of human speech delivery. When successful, TTS systems can not only deliver information, but also connect with listeners on an emotional level, which is especially important in healthcare, education, or customer service contexts. Latency is one of the most important practical concerns in speech pipelines. When people speak with one another, they expect near immediate responses. A delay of even a second can disrupt the natural rhythm of conversation, making interactions feel stilted. In AI systems, latency is introduced at multiple points: the time it takes for ASR to transcribe, for diarization to separate speakers, and for TTS to synthesize speech. Optimizing each stage is essential for real-time applications, such as live translation, captioning, or interactive assistance. Some solutions involve streaming approaches, where partial transcriptions or audio are generated before the full input is complete. Others involve compression and efficient algorithms that reduce processing overhead. The ultimate goal is to minimize lag without sacrificing accuracy or naturalness, maintaining the illusion of fluid dialogue between human and machine. Integrating ASR, diarization, and TTS into a seamless pipeline requires careful engineering. Each component must pass data reliably to the next, and errors must be managed gracefully. For example, if ASR misrecognizes a critical word, the system may need to clarify with the user before generating a misleading response. Synchronization also matters. Diarization labels must align with ASR transcripts, and TTS must generate responses without noticeable delay. The challenge lies not just in building high-performing components, but in orchestrating them into a cohesive system. Integration also requires scalability, as pipelines often support many users simultaneously. The best designed systems make this complexity invisible to users, who simply experience smooth, natural interactions. Evaluating ASR performance often centers on the metric called word error rate, or WER. This measures how many substitutions, deletions, or insertions occur in a transcript compared to a human annotated reference. While useful, WER does not capture the full story. A transcript with a low WER may still misrepresent key terms or misunderstand specialized vocabulary. Developers therefore complement WER with targeted evaluations such as entity recognition accuracy or domain-specific performance. This ensures systems are not only statistically accurate, but also practically useful. Measuring ASR quality is about more than numbers. It is about whether the transcript supports the tasks and contexts for which it is intended. Evaluating TTS requires different approaches. Since intelligibility and naturalness are subjective qualities, human judgments remain central. One common method is the mean opinion score, where listeners rate generated speech on clarity, pleasantness, and realism. Objective measures such as intelligibility tests and latency metrics complement these subjective ratings. Together, they provide a comprehensive picture of system quality. For instance, a TTS engine might be fast and clear but lack emotional nuance, while another may sound expressive but respond too slowly. Evaluations help strike the right balance for the intended application. A navigation system might prioritize speed, while an audiobook reader must focus on naturalness and expressiveness. Scalability defines whether speech pipelines can function in real-world enterprise contexts. Handling a few audio clips in a lab setting is vastly different from processing millions of hours of speech in production. Enterprises such as call centers, transcription providers, and video platforms require systems that scale horizontally, distributing workloads across servers while maintaining accuracy. Storage is another consideration, as retaining large audio archives raises costs and compliance concerns. Scalable design ensures that speech pipelines do not crumble under volume, but continue to deliver reliable performance regardless of scale. In this way, scalability turns speech processing from a research capability into a dependable backbone for global operations. Bias and fairness pose enduring challenges. Studies have shown that ASR systems often perform worse for speakers with non-standard accents, regional dialects, or underrepresented languages. This discrepancy can lead to exclusion, frustration, and even discrimination. In workplaces, inaccurate transcription of some voices but not others undermines equity. Fairness also applies to TTS, where systems may offer more expressive voices in dominant languages while neglecting others. Addressing bias requires deliberate inclusion in training datasets, evaluation across diverse demographics, and mechanisms for continual improvement. Speech technology must serve all users equally, not just the majority, if it is to fulfill its promise as a universal medium of interaction. Security is paramount when speech systems process sensitive content. Conversations often include private financial details, medical records, or personal identifiers. Protecting this data requires strong encryption, strict access controls, and compliance with regulations such as GDPR or HIPAA. Observability features like logging and auditing must balance accountability with privacy, ensuring that monitoring does not itself expose sensitive information. Adversarial risks, such as spoofing attacks that mimic a person's voice, add complexity. Systems must be hardened to detect and resist such attempts. Security cannot be an afterthought. It is the foundation of trust. Without it, the adoption of speech pipelines in sensitive sectors becomes impossible, no matter how accurate or natural the technology. As organizations adopt speech pipelines more widely, their importance grows beyond technical novelty into essential infrastructure. They enable hands-free accessibility, power transcription services, support compliance monitoring, and drive real-time communication with digital assistants. At the same time, they face constant tension between accuracy, speed, cost, and fairness. Each factor must be managed without compromising the others. The story of speech pipelines is one of integration, weaving together recognition, structure, synthesis, and security into coherent systems that bridge human and machine communication. Their success will increasingly shape how people experience AI in daily life, not as abstract tools but as conversational partners embedded in workflows, services, and everyday environments. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Streaming automatic speech recognition is one of the most important advances for making speech pipelines usable in real-time contexts. Traditional ASR systems wait until a person finishes speaking before producing a transcript, but streaming systems deliver partial transcriptions as the audio is still being received. This creates the experience of immediate responsiveness, which is vital for interactive use cases such as live captioning, voice assistance, or real-time translation. For example, a streaming system might display the words, "Good afternoon, everyone," on screen before the speaker has finished the phrase. This not only provides instant feedback, but also allows downstream systems to prepare responses faster. The trade-off, however, is that partial transcriptions may be revised as more context arrives, leading to occasional corrections midstream. Still, the benefits of responsiveness generally outweigh the drawbacks, especially in accessibility and conversational applications where speed and fluidity matter more than perfection. Batch ASR, by contrast, processes audio recordings after they are complete. Instead of focusing on speed, batch systems prioritize accuracy and coherence. By analyzing the entire recording, they can take advantage of broader context to reduce errors. For instance, if a technical term appears multiple times in a lecture, batch processing can ensure consistent transcription across all occurrences. Batch ASR is widely used in media transcription, legal depositions, and compliance workflows where precision outweighs the need for immediate results. The choice between streaming and batch ASR depends on the task. Real-time communication favors streaming, while archival or professional documentation favors batch. Many organizations adopt both, using streaming to support live interaction and batch to refine and correct transcripts afterward. This dual approach balances responsiveness with reliability, ensuring that transcripts meet both immediate and long-term needs. Multilingual ASR reflects the global demand for systems that can recognize and transcribe speech across many languages. Businesses, schools, and governments operate in multilingual contexts where single-language systems fall short. A global enterprise might require support for English, Spanish, Mandarin, and Hindi, often within the same call center. Multilingual ASR systems are trained on diverse datasets spanning multiple languages, accents, and scripts, enabling them to switch seamlessly between tongues. Some models can even handle code switching, where speakers alternate between languages within a single conversation. This capability is transformative for accessibility, allowing multilingual communities to participate fully in digital communication. Yet challenges remain. Many languages are underrepresented in training data, leading to unequal performance. Addressing this requires targeted collection efforts and partnerships with local communities. True multilingual inclusivity is not just a technical feat, but an ethical commitment to global equity in speech technology. Domain adaptation enhances ASR performance by tailoring systems to specific vocabularies and contexts. General-purpose ASR models may stumble over specialized terminology in fields like medicine, law, or engineering. By fine-tuning models on domain-specific corpora, developers improve recognition accuracy for critical terms. For example, in medical transcription, a system must distinguish between ilium and ilium, terms that sound similar but have entirely different meanings. Similarly, in legal contexts, accurate recognition of Latin phrases is essential. Domain adaptation ensures that ASR does not simply transcribe words but does so with contextual awareness. This customization transforms speech systems from general assistants into specialized tools, capable of supporting professionals in high-stakes environments. Domain adaptation also boosts user trust, since repeated misrecognitions of key terms quickly erode confidence in the system's reliability. Advances in neural text-to-speech have paralleled those in ASR, creating voices that are nearly indistinguishable from human speakers. Transformer-based models, such as Tacotron successors and diffusion-based synthesis approaches, have made speech outputs smoother, more expressive, and adaptable. These methods capture nuances of prosody and rhythm that earlier concatenative or parametric systems could not. Users can now hear synthetic voices that pause naturally, emphasize important words, and even convey subtle emotional undertones. Such progress makes TTS suitable for more than functional tasks like navigation directions. It is now used in audiobooks, news reading, and entertainment, where expressive delivery is critical. The advance of neural TTS has transformed machine speech from a technical novelty into a medium capable of engaging human listeners on an emotional level, strengthening the bond between user and system. Voice cloning introduces powerful new possibilities, but also significant ethical concerns. By training on recordings of a specific person, systems can generate synthetic speech that closely replicates that person's voice. For positive applications, this can restore voices to individuals who have lost the ability to speak, preserving their unique identity. It can also personalize virtual assistants, creating voices that resonate with users emotionally. However, cloning also raises risks of misuse. Synthetic voices can be deployed in impersonation scams, misinformation campaigns, or unauthorized reproductions of public figures. This dual potential makes voice cloning a focal point for policy debates and technical safeguards. Watermarking, authentication protocols, and ethical guidelines are being explored to prevent abuse while preserving beneficial uses. Voice cloning illustrates the broader tension in generative AI between empowerment and risk, where careful governance is as essential as technical progress. Latency optimization is an ongoing challenge in building responsive speech pipelines. Each stage ASR, diarization, and TTS introduces delays which add up to the total time between a user speaking and hearing a response. Optimizing latency involves both algorithmic improvements and system-level engineering. Techniques include streaming transcription, efficient neural architectures, and parallelized processing. Infrastructure choices, such as deploying models at the edge rather than in centralized data centers, can also reduce delays. For applications like real-time translation or conversational agents, latency optimization is not optional, but fundamental. Humans are acutely sensitive to pauses in dialogue, and even slight lags can disrupt the sense of natural interaction. Successful systems aim to reduce latency to near-human conversational levels, creating interactions that feel immediate and fluid. The goal is to make technology fade into the background, allowing users to focus on communication rather than waiting for machines to catch up. Compression and bandwidth management play crucial roles in scaling speech pipelines for large populations. Audio is data-intensive, and transmitting raw signals quickly becomes impractical. Compression algorithms reduce the size of audio streams without significantly degrading quality, enabling efficient real-time processing across networks. In distributed environments, such as global call centers or cloud-based transcription services, bandwidth optimization ensures that systems remain responsive even under heavy demand. Techniques like adaptive bitrate streaming adjust quality dynamically based on network conditions, balancing clarity with continuity. Efficient compression makes speech pipelines more accessible by reducing infrastructure requirements, ensuring that they are not limited to regions with high bandwidth connectivity. As speech systems become more widespread, compression and bandwidth strategies will be as central to performance as the recognition and synthesis models themselves. Applications in accessibility highlight the social importance of speech pipelines. For individuals who are deaf or hard of hearing, real-time captioning provides access to conversations, classrooms, and events that might otherwise be exclusionary. For those with visual impairments, TTS enables access to written content, from emails to ebooks. Speech assistants empower people with limited mobility to control devices hands-free. In education, transcription services support students by providing searchable lecture notes. These accessibility applications demonstrate that speech pipelines are not merely conveniences but tools of empowerment. They expand participation in society, reduce barriers, and foster inclusion. Each improvement in accuracy, latency, or naturalness translates directly into greater independence and opportunity for individuals who rely on these technologies daily. Enterprises are also major adopters of speech pipelines, leveraging them to improve efficiency, compliance, and training. In customer support, call transcription and diarization enable quality monitoring and analytics at scale, helping organizations measure service performance and identify common customer concerns. In compliance, automatic recording and transcription of financial or legal conversations provide traceable records for audits. In training, synthetic voices allow for scalable e-learning content that can be adapted to multiple languages and styles. Enterprises view speech pipelines not only as operational tools, but as strategic enablers that transform voice data into actionable intelligence. By automating what was once manual listening and note-taking, organizations unlock new insights and efficiencies, positioning speech technology as a cornerstone of digital transformation. Evaluation benchmarks provide standardized ways to measure progress in ASR and TTS. Datasets like LibreSpeech, Tedlium, or Common Voice allow developers to compare systems objectively on recognition accuracy. Benchmarks for TTS often involve subjective evaluations, but datasets with aligned audio and transcripts help test expressiveness and clarity. Benchmarks are not just academic. They guide industry by establishing transparent measures of performance. They also expose limitations, showing where systems still struggle with accented speech, noisy conditions, or expressive synthesis. Continuous benchmarking ensures accountability, preventing inflated claims, and grounding progress in shared standards. By evaluating consistently, the field advances collaboratively, with improvements benefiting all stakeholders. User trust is perhaps the most intangible yet essential factor in the adoption of speech pipelines. Trust arises when systems consistently deliver accurate, intelligible, and safe outputs. Errors in transcription, robotic-sounding voices, or privacy breaches quickly erode confidence. Conversely, systems that demonstrate reliability and respect for users earn loyalty and adoption. Transparency is key. Users should know when speech is being recorded, how it is processed, and what safeguards are in place. Clear communication about limitations also builds trust, setting realistic expectations. Ultimately, trust is not built by technology alone, but by the relationships organizations cultivate with users. Respect, reliability, and responsibility together ensure that speech pipelines are not only technically sound but socially accepted. The future directions of speech technology point toward deeper integration with multimodal AI. Speech is rarely isolated. It coexists with text, video, and gesture in human communication. Future pipelines will connect seamlessly with video understanding, enabling systems to analyze conversations in context with facial expressions or body language. They will also integrate with chat agents, allowing speech inputs and outputs to feed directly into broader reasoning and planning systems. This convergence will create richer, more natural AI experiences, where voice is one of many channels in a holistic interaction. The pipeline metaphor may even evolve into a web, with speech, text, and vision interwoven rather than strictly sequential. This direction promises not just more powerful systems, but also ones that feel more human in their ability to perceive, understand, and respond. Cross-domain integration underscores how speech pipelines are already feeding into broader ecosystems. Voice inputs power chat systems, while transcripts inform search and analytics. Diarized conversations populate training datasets for customer service optimization. Synthetic voices narrate video tutorials or interactive simulations. The boundary between speech and other modalities is dissolving, with each reinforcing the other. This interdependence reflects the reality of communication itself. Human interaction is inherently multimodal. Speech pipelines serve as the entry point, capturing and producing voice, but their true value emerges when they connect to wider systems of knowledge and action. Integration ensures that voice data does not remain siloed but contributes to comprehensive, context-rich applications. As organizations expand their use of AI, video understanding emerges as a natural extension of speech pipelines. Just as ASR and TTS process spoken language, video systems interpret visual streams, combining movement, expression, and text on screen. Together, they create multimodal records that capture events in their full richness. For example, a meeting record may include not only who spoke and what was said, but also who presented slides, how the audience responded, and what visual cues were shared. This progression underscores the continuity between speech and video. Both are streams of human communication that demand careful capture, interpretation, and synthesis. Speech pipelines thus prepare the ground for broader multimodal understanding, where the spoken word is one vital layer in a more complex fabric of interaction. Speech pipelines, then, are best understood as the infrastructure that makes voice a usable and trustworthy medium in the digital era. They combine ASR, diarization, and TTS into cohesive workflows that power accessibility, enterprise analytics, and personal assistance. They must balance accuracy, latency, scalability, and fairness, while also ensuring security and transparency. As research advances, they are becoming faster, more natural, and more inclusive. Their future lies in integration with multimodal AI, where speech becomes one of many channels in human-machine communication. This trajectory highlights both the promise and the responsibility of speech pipelines. They extend human voice into the digital domain, but they must do so in ways that respect, empower, and protect users. By maintaining this balance, they will become foundational to the next generation of interactive, trustworthy AI. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.